to give this talk. So, the subject of the talk is about projective embeddings of some properties of projective embeddings of abelian varieties. Okay, so the setting will be, the notation will be X, will be an abelian variety, and A, an ample line bundle on X. So some classical results. Okay, so the first one is really very classical. If we take a power of A and we take at least a power, then this is very ample. This is due to Lefschetz. And so we have an embedding, a projected embedding of X in projective space. So the second class of results is about properties of the image, so the embedding. So we have that X is projectively normal if n is at least 3, and the homogeneous ideal is generated by quadratic equations. If so, we have at least a fourth power, and in the case of third power, we need quadratic equations and cubic equations. Okay, so these are results of the 70s due to Koizumi and Mumford, with I think a slight addition of Kempf. Okay, so what I will discuss today is some developments of this line of research. So in two directions. So the first one is to hire Syzygies. And second one is extension of this type of results to line bundles which are not the power of a high power of a smaller line bundle. So these are called primitive line bundles. So primitive means not the power. Okay, so let's start with the first topic. So here the notion is the important notion is the so-called property NP due to Margrim. So let me remind what it is. Okay. So we have here in general, so that's a notion that can be given, of course, in general. So we have X, a projective variety. It might be also singular. And L, a very ample line bundle on X. Then we have the ring of sections associated to L. So it is the direct sum of various powers of L, and this is a modulo over the polynomial ring, which is the sum of symmetric powers, which not of L. So maybe this is not the same n as before, so let me call it k. So it is. So this R is a graded module over the polynomial ring. So you can. So there is the resolution. The resolution of R as graded module over the polynomial ring. Okay, so it looks like so what are properties NP? Property NP. It's like that. So here we have the beginning of the resolution. If the natural map from the polynomial ring to R is surjective, so the resolution, the beginning of the resolution is like this. So this is called. So this is projective normality, and it is seen as the first step of a hierarchy of conditions. This is called the condition N0. So this is projective normality. Now, if this condition holds, the kernel here is the homogeneous ideal, and if it is generated by quadratic equations, this is called condition N1. So this is quadratic equations. So these are the two conditions of the theorems of Koizumi and Mumford. And the next one, we can consider the relations between these equations, and if they are generated by linear ones, so here we have only degrees equal to, homological degree equal to 3, this is called property N2. Linear relations. And so on. So then we can arrive to a generic fifth step, and if the relation continue to be linear up to the, so this is the P step. This is property NP. NP. So NP means N0, so projective normality plus.
It means that if you take a minimal resolution, it just means that the last step is what you say.
Yes. So this is, of course, a minimal resolution.
Yes. And then you only need to.
Yeah, and it means that it is projectively normal. The homogeneous ideal is generated by quadratic equations, and the Syzygies are linear up to the step P. So N0 plus N1 plus linear Syzygies up to the P step. Okay. So these conditions NP starting from N2 are kind of extensions or generalizations of projective normality and so the theorems of Koizumi and Mumford. So they were introduced by Green in the 80s, who showed in a series of remarkable theorems and conjectures that, at least for the case of curves, they are really natural and useful generalizations of these two classical conditions, N1, two conditions which were studied classically, N0 and N1. So Green in the 80s showed that four curves showed in a series of theorems and conjectures, partly in collaboration also with others, that four curves, these are really useful generalizations of the classical conditions N0 and N1 appearing in classical theorems due to Noether, Castelnuovo, and Petri. Okay, so it is natural also to study these conditions in higher dimension, and at least in the case of abelian varieties, they are also in some sense natural generalizations, something which is natural to study. Okay, so let me state some results here. So the first theorem that is due to me is an extension to these conditions NP of the theorems of Kodumi and Mumford. So I take a line bundle, so let X an abelian variety. So I consider a power of a line bundle, L of the form equal A to the n, and if the power is at least P plus 3, then L satisfies NP. So this is, for the cases P equal to 0 and 1 recovers the theorems of Koizumi and Mumford. And so this statement was conjectured by Lattersfeld. So there are also, there are variants of these statements, some related problems. So, for example, one could ask what happens. So, okay, so this is sharp. Is sharp if one takes the smallest possible A. So these are principal polarizations. So it's sharp for H0 of A equal to 1. So principal polarization. So this is shown also in the theorem of Mumford. So if you take a fourth power, the homogeneous ideal is generated by quadrics, but if you take a third power, it is not generated by quadrics, and you need cubics. Okay, and so if you assume that A is slightly more positive than a principal polarization, one gets a little more. So another theorem that I obtained with Poppa is that if A, so if the base locus of A is not a divisor, there's no base divisor, so one can improve of 1 these bounds, and so n is bigger or equal than p plus 2, then one gets np. So for example, for the case p equal to 0 was also classically known. For p equal to 0, so we have a square of a line bundle, and so if A has no base divisor, then A square is very ample, in fact, and projectively normal. This is a theorem of also of the 80s of Obuchi. Obuchi. Okay. So a more recent, so these were results obtained already a few years ago. So a related question is about Kummer varieties. So for Kummer varieties, I mean the singular ones. So again, X is an abelian variety, and I take the quotient under the involution sending X to minus X. This is the Kummer variety. And then
A should be linearized, should be symmetrically bundled.
yeah. So yeah, I take a L, say an ample line bundle on the Kummer variety. So here I have the quotient. So it turns out that its full back on the abelian variety is in fact, as Fabrizio was saying, is the square of a symmetric line bundle. So then what happens is that the ring of sections, so it is, we said, the sum. So the sections are identified to the invariant sections of the line bundle, of this line bundle here, the L squared. So it is the sum of H naught of L2K plus, and of course, so the polynomial ring is the sum of the symmetric powers of H naught of L2 plus. One can, of course, ask the same questions, and so so a result with my student Sofia Tirabassi is that a similar result. And so I take L, which is a power of n. So if n is bigger or equal than, so p plus 3 over 2, so then we have np. So this generalizes also some, for p equal to 0, it is a result of Sasaki. But I should say that in fact this is a recent result, maybe it's too recent because in fact it is still not completely proved. So to be confirmed. So there are still some problems in the proof. So this is a related problem, a related result. And I have, so maybe I should say why I do like this type of problems. So my experience, what happens is that even if these conditions NP, so the definition seems very algebraic and somewhat cumbersome, so kind of very algebraic, sometimes artificial. But so what happens is that.
Can I ask a question to the sharpness? Yeah. If you take the Kummer quartic surface, so that's the case p equals 0, that you want projective normality.
Yeah.
Then there you want 3 halves, but 1 is enough.
No, it is not always projectively normal.
It's not always, I see.
Yeah, the surface, yes.
Okay.
Yeah, the surface,
okay,
yes, but in higher dimension.
In higher dimension it's not projective.
Yeah, it depends on the fact that there is certain vanishing theta nulls or not. Yeah. For example, in dimension 3, it is a Jacobian, so it is projectively normal exactly if it is not a hyperelliptic Jacobian.
Okay, thank you.
Yeah. So, yeah, so So in my experience, what happens is that the passage from equations, so the principle of Green is that equations should be seen as particular cases of syzygies. But then in practice, what happens is that when you try to extend the methods that classical methods for equations to syzygies, they usually don't work. They lead to very intricate computations that become more and more difficult. And so what happens in practice is that to prove these very algebraic conditions, you need to usually to find more geometric proofs also of the classical statements. For example, the classical statements of Koizumi and Mumford, they are proved with theta functions. So in a very algebraic type of computations, you write down bases of the spaces of sections, and you prove the surjectivity using these bases. But then these computations don't extend to syzygies, and so you need to find a more geometric argument, which avoids the algebra of theta functions. So that's.
But I mean, in the Varena Chime notes, Mumford had given up using theta function. He had more.
Yeah, but I think that still the proof of the Mumford theorem uses theta functions. And it is coupled with a more geometric argument, but the basis, I think, is this. So I was saying that the reason why I like this problem is that even if they are very algebraic, you usually need a more geometric understanding of these kind of statements. Because the usual algebraic methods, they lead to too intricate computations. Okay, so now so I would like also to illustrate some of the methods used in proving this type of theorems. So, but before doing that, let me say something about the primitive case. So here the situation is much more difficult, and it is somewhat more similar to other varieties, different from abelian varieties. For example, these statements here, they are independent on the dimension. So they are the same bounds in every dimension. This is very peculiar for this type of problems on abelian varieties. So here on primitive line bundles, everything is much more difficult. So and we know much less about that. So, okay, so we have L. To L it is associated a sequence of numbers which appear when one diagonalizes the C1 of L, C as a form. Divide this divided d2 dg, and so the H naught of L is the product, is D is the product of these numbers. Sorry, this is a G. So G is the dimension. And so here, already not much is known about variampleness. So what one expects, so it is expected that for D bigger than a certain linear function of G, which is expected to be 2G plus a constant, then the general abelian variety with L of type d1 dg with d1 dg equal to D, then the general line bundle is very ample. So here the fact that we have to take the general already shows that the situation is much more difficult.
The bar has some result in this direction, right?
Yeah, yeah. Yeah, then I will list what is known, I will say what is known in this field. So one needs to take general, because otherwise it's easy to find counterexamples. For example, you take a variety, type 1D, so if you can take a product of elliptic curves, and this one is a line bundle of degree 1 or one of the elliptic curves, D is a line bundle of degree D on the other elliptic curves, and so it can never be very ample, even if you take D very big. So you have to take general.
But I mean, can't you just restrict to the something which is not a product?
Yeah, I don't know. I don't think so.
In the statement before,
yeah.
you said there is no base locus which is a divisor.
Yeah.
That happens exactly when it splits
Yeah,
as a
no,
product of a principally
yeah.
polarized and something else.
No, I
Splits
think-
as a pair.
Yeah. No, I think it's more complicated, but I don't know. I think it's more complicated. Yeah. So what is known is so what are known are exponential. So for surfaces, one knows the optimal results by the Ryder theorem, and but in general, what are known are just exponential bounds. So probably the best exponential bound is for line bundle of type 1, 1, 1, say D. So if this D is bigger than 2 to the G, then the general is very ample. This is due to, I think, to the bar, Ulek, and Spandau. So you see that. So what we know in this field is much less than what we expect, and again, within this sort of exponential bounds, there are results of the type I was illustrating before, so about projective normalities and Syzygies. So a recent result of last year of Wang and To says that if D, which I remember is DH not of L, so sorry, D is bigger or equal than 8G to the G divided by 2G factorial, which can be approximated to more understandable 8e to the G.
Sorry, is 2G factorial or 2G factorial? As you wrote.
2
Okay.
times G factorial. So divided by 2 can be, so it's something like 8e to the G. Then have projective normality. And this was extended to Syzygies by in the theorem of Lazarsfeld, myself and Poppa. So if D is bigger or equal now of 4p plus 2 to the G, no, times G to the G divided to G factorial, so which is something like 4p plus 2 G to the G divided by 2, then we have condition NP. Of course, for the general line bundle. For the general line bundle. For the, say, the general pair XL with L of type D1 times comma comma DG with the product of these indices equal to to D. Okay, so now,
Sorry, there it's 4p plus 2g.
yeah,
That's not correct, because for p equals 0, it should give e.
sorry, E.
Yes.
So the G was here. Then, yeah, there is an approximation due to a formula called the Stirling formula about
You know,
G factorial.
to the g.
Okay, so I will now in the second half I will try to illustrate the methods in both cases. So first the case of power line bundles, which are powers of a smaller line bundle, and then primitive line bundles. So roughly speaking, the methods for powers are somewhat based on the Fourier-Mukai transform for abelian varieties, and while the methods for primitive line bundles, so they are very much more similar to the other varieties, are based on vanishing theorems. Okay, so the case of powers. So here, the natural thing is to use reducible sections. So that's how the left-shift theorem is proved. So you have a third power, and you show that reducible sections, which are made of the union of three translates of theta, say, they separate points and tangent vectors. So that's, of course, you make advantage of reducible sections. So you want to use reducible sections. So kind of an efficient way of doing that is in the following definition. So we have this notion. We have so let F be a sheaf on an abelian variety. We say that so it's kind of a weakening of the notion of global generation by global section. So F is said CGG, which means continuous global generation. Of course, it is a local notion, so at the point X, if for every open set in the peak zero, so in the dual abelian variety, so what we do, we take the sum for line bundles in U of this twisted evaluation map. So F tensor alpha dual. So if we evaluate this, we end up in F tensor alpha dual, but then we tensor with alpha, so we end up in F. And so if this map is surjective, so if we want the local, so at the point X, say, then this is, it's called continuously globally generated at X. Now, so this is a way of using reducible sections, because it is an easy exercise that if we take a continuously globally generated sheaf and we tensor it with an ample line bundle, we get a globally generated. So easy. It's an easy exercise that if F is CGG at X and A is ample, we are on abelian varieties. Then F tensor A is Syzygies. Say X. So in this way, so this means that F tensor A is generated.
CGG at X or at each point?
Sorry, is GG I wanted to say. So if
But at each point?
Well, there is a local version. So if it is CGG at X and A is ample, then it is globally generated at X. And of course, at each point, if the hypothesis, if it is continuously globally generated everywhere, then if tensor with an ample, it is globally generated everywhere. So then, so the meaning is that so how you solve these exercises, you show that F tensor A is...
So I'm confused. I mean, if something is continuously globally generated at X, then it is...
No, it is not globally generated at X.
Ah, okay, sorry.
Yeah, there is the sum. So it means continuously globally generated means that...
I copied it wrong. Okay, sorry.
Yeah.
Now I did.
Yeah, it means that the sections of these various... So the twisted sections of these various things, they span each file.
It, so I thought it was a
so then
tensor
F tensor A is generated by reducible sections, like say S minus alpha times T alpha, where this is in H naught of F tensor alpha dual, and this is in H naught of A. So this is a way of using, this way of using reducible sections. And okay, so now the Fourier-Mukai transform appears when we want to give a criterion for being continuously globally generated. So we have this theorem saying that if certain vanishing conditions is satisfied, then Schiff is continuously globally generated. So the vanishing condition is this. So I will state it in its easiest form, which is also the one which is used in the Syzygies theorems. But then this condition, the hypothesis can be relaxed in various ways. So, but I will not insist on this. So that's the somewhat the easiest version. But so if all the higher homology groups of F tensor alpha are 0 for each positive I and for each alpha in the peak node of X, then F is continuously globally generated everywhere.
It's not sufficient an open set in peak 0.
So it can be relaxed. So to a condition which was introduced by Poppa and myself, which is called M regularity, which is so the hypothesis can be relaxed to this condition which says that the codimension of the locus of alphas such that the HI is bigger than 0, HI of F tensor alpha is positive, the codimension is bigger than or equal, strictly bigger than I for each positive I. So this is called M regularity. And under this assumption, still the conclusion is that F is continuously globally generated everywhere. And then it can be also further relaxed with bigger than or equal here rather than strictly bigger. And this has also a kind of boring name called the GV, generic vanishing. But this is not always true. So so then the statement of the theorem is becomes more complicated. Okay, in fact, these conditions, these vanishing conditions, so I don't have time to insist much on this, also because they are not very relevant to, so they have applications to other geometric problems, but not especially to Syzygies. So these vanishing conditions have a meaning in Fourier-Mukai theory. So this condition here is called the I index theorem of index 0. So it means that it means that the transform, the Fourier, as we will see, the transform of f, the Fourier transform of f is a sheaf, and not only that, is a locally free sheaf. While this condition here, M regularity, means that the transform of the dual of f is a sheaf and actually a torsion-free sheaf, while the one that I didn't write, so the weakest, means just that the transform of the dual is a sheaf, which might have also torsion. So these are kind of relevant conditions. So, okay, so how, so what is the idea of proof of this theorem? So the proof actually is not really, so during the years then we understood better the proof. Now the proof is not really a proof but only a remark. So let me recall what is, so uses the Fourier-Mukai transform. We have here the abelian variety X, the dual abelian variety, and the two projections. So this is the classical Fourier-Mukai transform, which is made with the Poincare line bundle on the product. So now, okay, then so this transform is, so we take a f, a sheaf, or more generally an object in the derived category on X, and we pull it back, we pull it on the product, we tensor with P, and we push it down on the dual variety. And so this is called, so our hat S of F. So this RS hat is a functor from the derived category of X to the derived category of P0 of X. And there is the same, so defined in the symmetric way, we can define a functor from going back from the dual variety to X. And so Mukai's theorem says that these two functors are essentially inverse to each other. For example, RS composed with RS hat is just, so it's not the identity, there is the involution here, so multiplication by -1, so almost the identity. So you get, so if you start with F, you get back F just so modified by the involution and in cohomological degree G. So they are essentially inverse to each other, so in particular they are equivalences. And so how do you use this in relation with continuous global generation? So now I'm kind of running out of time, so I can't go into much detail, but the idea is it's actually so we start with our F. Then the hypothesis, which was the vanishing of all these homology groups. So this means that when we take this transform here, we don't have the Ri's with I bigger than 0, we have only the R0. just because of Grauer theorem on base change. So this R S hat of F is just the R0 of F, and this is denoted it is a notation usual in Fourier-Mukai theory as F hat, and it is also locally free, again by Grauer's criterion. Then, so what happens is that the Fourier-Mukai transform identifies the evaluation map. So let's take, for simplicity, I take a point x equal to the origin. So for simplicity, then I have my funny evaluation map here to say f at 0. Now this has to factorize also through as a shift to k of 0. So this, it identifies the dual of this evaluation map. So also to an evaluation map. So this map dual is identified by Fourier-Mukai to the evaluation map of the dual of the dual of the transform, which evaluates to the point corresponding to the point. So now this is something which lives in the dual abelian variety, and so this alpha is a line bundle on F, so it is a point of the dual abelian variety, which I will denote with this symbol here. Okay, so by Fourier-Mukai, the dual of this map is identified to this. So this is the point parameterizing the point in peak 0 of x, parameterizing alpha.
So F hat is a vector bundle.
Yeah.
Of higher rank. Okay.
Yeah, it is a vector bundle. Also the dual. So yeah. So now, because of this, so this is a kind of an exercise when you write down the transform explicitly, and so we have that the sum of these evaluation maps, say tensor of k0 to say f tensor k0. So the dual is identified with the evaluation map of the dual of f hat. So this goes on the various points Okay, so now we have to prove that this is surjective. So for alpha varying in an open set, so here I should write an open set rather than pick 0. So surjectivity knows this means injectivity of the dual. But then this is clear because we have a torsion-free sheaf, so a section which is non-zero is non-zero on any open set because it's torsion-free. And so this map is clearly injective, and so this is surjective.
But I mean, for injectivity, you don't need to take an open set, sufficient a point.
What?
For injectivity, it's sufficient. Okay. Because you take the value, okay.
So surjective, because so it is. So this is injective. Sorry, the dual injective, since So this is the map taking a section to the evaluation to each point. So it is always different from 0 on an open set. Since f to all hat is locally free, so torsion free. Yeah, so the proof also shows that if you have a cohomological condition guaranteeing that you get the torsion freeness, then the argument works. And so this is responsible for the weakening that I was alluding to before. Okay, so this is the idea of the proof of the cohomological condition. Then how do you apply this to Syzygies? So now, for application to Syzygies. Okay, so here there is a fact. So there are kind of standard theory due already to Green about Syzygies that if a certain condition holds, so the condition is that the multiplication map of a certain vector bundle, which I will write and then I will define. So surjects on the target. So this multiplication map is.
So is that before? It's a tensor product or what? Or a sum?
Okay, so here we have now. ML is by definition the kernel of the evaluation map, so it is called the evaluation bundle sometimes. So we have this, the tensor product of P copies of this vector bundle times L, and then you
But why this? What is the tensor product to the left?
This it is the tensor product of ML times ML.
Yes, I did it. Okay. Okay.
P times, and then you take so this map. So if this is subjective, then NP holds. So this is a standard fact about conditions NP already due to Green. Then, so we are reduced. So the problem now, we have this complicated vector bundle here. So we are reduced to study the subjectivity of multiplication map of global sections, say H naught of F, tensor H naught of L, in H naught of the tensor product. In this case, F is this thing here, but it is, of course, you can state it more generally. You can maybe put in the hypothesis that F is locally free. Okay, now, this is, in fact, for abelian varieties, this is a global generation property. Because you can see this map here. So this is just the H0 of the external tensor product, say F external L, which restricts on the diagonal. And so this, of course, general fact, but on abelian varieties, you can see this as a global generation property, because you can identify this to, so you take the difference map, and then, the source is the H naught of D lower star of say F external L, and the target is So the restriction to the fiber of D, so you can see it at least under some base change hypothesis to as the fiber at 0 of D lower star external L. Okay, so it is a global generator. So it is a global generation property. Global generation property. So we can apply the previous theorem. And so I'm checking that HI, so checking that HI of this D lower star of F external L tensor, say A to the -1 tensor, say alpha dual, are all 0 for each alpha and for each positive I, where F is the tensor product of the MLs tensor L, and L is the n power of this for n, say bigger or equal than p plus 3. So the checking of this is already another business. It's not easy, but somewhat conceptually more simple than the previous step. So it uses some tricks with abelian varieties and semi-homogeneous vector bundles on abelian varieties. So this is more or less the idea of the proof of the results that I have stated before. Of course, the proof is not equal. So each variant has its difficulties. So let's go briefly in the last 5 minutes in the primitive case. So primitive line bundles. Okay, so since because of lack of time, I will just say a few things about this. So both proofs of the result of Wang and Tu and the result with Ladersfeld and Popper, they use the Syzygies constant. So we have our line bundle of type D1 DG. D is H not of L, is the product of these numbers. So this D is not by itself an efficient measure of positivity of L, because we saw that at least in the case of the product, we have kind of we don't have what we want. So we have to. So the idea is to use another measure of positivity, which is called the Syzygies constant. So it is defined as at the point x. It is a local notion. It is defined of the maximum of real numbers lambda, such that so if we blow up. So now I will write this math, where this pi is the blowing up at the point x of the variety, the canonical morphism, and E is the exceptional divisor. Okay, now this is a local notion, but for abelian varieties it's easy to see, since it is also a numerical notion, that it doesn't depend on x. So we have just a epsilon of L, and so this is a kind of difficult and delicate invariant and very difficult to evaluate. So for abelian varieties, it's kind of a lucky case. So there is an estimate of these numbers, So we have another invariant which is defined as follows. So the Buzek-Sarnak invariant. So here we see the abelian variety as a complex torus. And so the Buzek-Sarnak invariant is the minimal length of a period so for lambda of the squared length of period with respect to the geometric Hermitian form corresponding to C1 of L. So it is an Hermitian form on CG, and so there is an estimate. So this Buzek-Sarnak invariant can be somewhat estimated. So we have that ML is bigger or equal than a certain number, which is I think it is the g root of 2d g factorial over pi. This is due to Buzek-Sarnak for principal polarizations, and to Thomas Bauer for in general. And then, so there is another theorem of Lazarsfeld which compares the Seshadri constant to the Buzek-Sarnak invariant. So the result is that this is bigger than pi over 4, the Buzek-Sarnak invariant. So putting everything together, you have that L is bigger or equal than, I think, the general. Yes. Okay, so if the Seshadri constant is bigger or equal than, no, strictly bigger, I say, than 2g, then we have N0, so which is the projective normality. And so if you plug these estimates into this, you get that if d is bigger or equal than something which can be approximated to the same bound of, so 8e to the g divided by 2, then we have N0 for the general. And so the result with Lazarsfeld and Popper is a generalization of this with a slightly simpler proof. So if this is bigger than p plus 2g, then you have NP. And so if you plug the estimates for the Seshadri constant, you get that if this is, then you get NP for always for the general. Okay, so now I have finished. Of course, in the proof one reduces the condition NP to a certain vanishing theorem of a line bundle times a certain ideal of diagonals, of union of diagonals in the product of the abelian variety with itself, the Cartesian product, many times. And then one checks this vanishing using either Kawamata-Vivek or Nadal vanishing, using, of course, the positivity of the line bundle. Okay, so, thank you.